Good everyone, welcome back to class. Today we are going to be looking at a very important topic in physics, which is electric field. Now, what is the meaning of electric field? Before we go to the definition, please, if you know you have not subscribed to this channel, please try and do so, and distance yourself away from anything called distraction, because you are going to gain a lot from this class. Because of that, you know something like afford to distract yourself by any means. Please and please don't skip any part of this video, because every second of this video is very important, it's highly vital. So please and please watch this video from the beginning to the end. Don't skip any part, because after this video you are going to be a sound student when it comes to the concept electric field, because I'm going to take you guys through electric field lines, electric field due to dipole, several charges, a sphere, and electric field due to charge this, charge ring, and the rest. So please and please don't distract yourself. Don't distract yourself. Watch this video from the beginning to the end. Now, how do we define an electric field? What is the meaning of electric field? Electric field can be defined as a region of space in which electric force can be felt. Electric field is just a region around a charge where you can feel electric force. Remember we said in our last class that, electrically charged bodies are bodies that can exert electric forces on the surrounding, and we have two forms of charge. A charged body can either be positively charged or negatively charged. Now, electric field is produced in a place where we have electric charges, because where you can feel electric force, we call that region electric field. So that is why I said electric field is a place where you can feel electric force, and you can feel electric force around an electrically charged body. Let's take a look at that. Now, the strength of an electric field, the strength or the intensity of an electric field is defined as the ratio of force to charge placed in the field. Is defined as force per unit charge experienced in that field. The force in which a charge will experience when it's placed in the field, we can measure our electric field strength from that definition. So electric field strength is force per unit charge, or force over charge, or the ratio or the quotient of force to charge. So that's why I said E in this place is equal to F over Q. Now this E is electric field strength. Is the strength of an electric field. It is defined as the force expressed in the field divided by the charge expressed in that force. So I can ask you, what is the force experienced by a particular charged body placed in so field? The force is equal to, now in this place now, force will be equal to, electric force will be equal to E times what? Times Q. That's how we define electric force here. Electric field times charge. So Fe, which is electric force, is equal to EQ. Electric field times charge. So this is the force expressed by a charged body placed in a particular field. Please don't forget that electric field are always present where we have electrically charged bodies. Electrically what? Charged bodies. And don't forget, charged bodies can be in two forms. So that we have positively charged body or what? Negatively charged body. Now this electric field we are talking about, which is force over charge, is a vector quantity. Is a physical quantity. There is a vector quantity, and the unit of electric field is Newton per coulomb. Newton per coulomb, or you can also use another unit, volts per meter. So look at this one when we are looking at electric potential, volts per meters. But I'll be using Newton per coulomb because the unit of force is Newton, unit of charge is what? Coulomb for electric field. And this electric field is a vector quantity. What is the meaning of a vector quantity? It's a quantity that has magnitude and what? Direction. And it also obeys Pythagorean law of vector addition. So electric field is a vector quantity in which we have magnitude and direction as well. So if you want to calculate the magnitude of a field, you can use this formula. Depending on, you can also use, we have electric field due to a point charge will be going to in a distant time. So now, what will be the direction of that field after we have calculated the field? The direction of a field can be obtained either from the concept of the electric field lines of us, or from the concept of the direction of a test positive charge placed in a particular electric field. Now, look at this. What we call electric field lines. Concept of electric field lines. Now, what's the meaning of electric field lines? Electric field lines are imaginary lines that determine the direction of electric field. It determines what? The direction of electric field. Now, these field lines, the electric field lines are drawn such that the tangent at any point will denote the direction of the electric field at that point. At that point. Now, the direction of electric field can also be obtained from the direction of a test positive charge placed in that field. Placed in that field. I'm going to explain everything one after the other. Now, from the concept of electric field lines, we have two forms of charge. Positive charge and negative charge. Now, positive means plus, negative means minus. Now, if you have a positive charge, we have the the properties of electric field lines. Now, one property is that electric field lines are always directed away from a positive charge and always towards a negative charge. Take note of that. Electric field will only leave a positive charge and it will always enter a negative charge. So this is a positive charge. That's why these lines denote electric field lines. This one denotes electric field lines. So for a positive charge, the field will be leaving. Remember, we draw a vector by a line with an arrowhead. The line denotes the magnitude, while the arrowhead denotes what? The direction. So the direction is going radially outward, 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 outward. So it's directed away from this positive charge. It's leaving the positive charge in layman language. Then, for a negative charge, the electric will be entering the negative charge. It will be coming towards the negative charge. Always directed towards the negative charge. And we can also use test charge to check for the direction of electric field. Let's say we have two charge bodies. Let's say we have two charge bodies. Let's say we have plus Q. Let's say we have minus Q. And let's say we have distance apart. I said, if you have a field line here, you have a field line like this, what will be the direction of this field line from this positive charge? Direction will be outward. Abi, if I want to use field line to take direction of electric field. What about electric field from this one? What will be the direction? Direction will be inward. Why is it inward? Because electric field lines will always enter or be directed towards the negative charge and away from the positive charge. So it's leaving the positive charge and entering the negative charge. Now, if I want to use the concept of test charge, if I say what the electric field velocity at this point, then you put a test positive charge at that point. We call it Q naught. I can just call it Q naught. Then you now check, how will this test positive charge, what direction is this test positive charge going to go due to this charge and due to this other charge? Remember from Coulomb's first law or electrostatic law of charges that like charges will repel each other, while unlike charges what? We attract each other. So based on that fact, the direction of the field at this point in which we have this test positive charge, this negative charge will attract this positive charge. Why? Because unlike charges we attract. So this one, this test charge will be attracted to this place. So field due to this one will be coming this way. But this test charge will be attracted to this place. Then what about the field due to this negative charge? The field due to the negative charge to this positive charge. Field due to the positive charge will also be repelling. This one towards this side. This one will be repelling it towards this side, so we'll be attracting it to itself. So you see, both of them are actually going to this side. You can also use that to get the concept, the direction of electric field. We'll get there later. But I love this electric field lines very well. Electric field lines will give you the direction in a very clear way without much explanation. Just know that electric field lines are always directed away from a positive charge and always directed towards what? A negative charge. And if electric field lines are something like, oh, if the field lines are very close to each other, the field will be strong. But if they are far apart from each other, the field will be weak. And electric field lines cannot cross each other since the direction of electric field is unique. And these electric field lines cut through the equipotential surface at right angle. Cut the equipotential surface at where? At right angle. At what? Right angle. Now, this and this are the same thing. Let's say we have a positive charge here, a negative charge here, we have a positive charge here, positive plus, negative minus. Now, electric field lines will leave a positive charge, will leave a positive charge, and will be entering what? A negative charge. So this is also a concept of field lines, You don't have to draw field lines. That is very, very important. Now, let's look at this question. Obtain the electric field strength, or electric field intensity, and obtain the electric field intensity when a force of 100 newtons, is experienced, by a charge, of 50 microcoulomb, when placed in the field. We are trying to obtain the electric field intensity when a charge of 50 microcoulomb experiences a force of 100 newton in this field we are talking about. Now, we said electric field strength, this is the force, and this is the charge, experiencing the force. Now, we said electric field strength is equal to what? Force over what? Over charge. Then, what is micro in physics? Micro is something like order of magnitude that has the magnitude 10 raised to the power minus 6. So 50 microcoulomb is said as 50 10 raised to the power minus 6 coulomb. 50 times 10 raised to the power minus 6, because 10 raised to the power minus 6 and micro is said as 10 raised to the power minus 6. That is the value for magnitude of micro. So we're going to have 100 divided by 50, so it's 10 raised to the power minus 6. So we're going to have 100 divided by 50 times, if this 10 moves up, this power will change to plus. That will not change to plus. If this 10 to the power minus 6 moves to the upper side, the minus will change to plus from indices. I'll be doing that in indices. Then 50 here 1, 50 here 2. So this will give us 2.0 times 10 to the power what? 6 Newton per coulomb. That is the strength of the field. Example 2. Calculate the force experienced by a charge of 10 microcoulomb. When placed in a field of 10 raised to the power 3 Newton per coulomb. Calculate the force experienced by a charge of 10 microcoulomb when placed in a field of 10 raised to the power 3 Newton per coulomb. So let's look at this question. Now, our charge here is equal to 10 microcoulomb. Then the electric field is equal to 10 raised to the power 3 Newton per coulomb. So this one is set here at 10 times what? 10 to the power minus 6, because micro is 10 to the power minus 6 and coulomb. Then we said F is equal to what? EQ is electric force. So this one will be equal to E is what? 10 to the power 3. Then Q is 10 times 10 to the power what? Minus 6. So remember it's 10 to the power 1. So if you apply this here, we're going to have 10. P come on the base, add up the power 3 plus 1 minus 6. That is minus 6. Now give us 10 to the power what? Minus 2 newtons. That is minus 2 newtons or 0.01 newtons. Also have 0.01 newtons. 0.01 newtons is 1 over 100. So this is what I will have. 10 to the power minus 2 newtons or 0.01 newtons. That will be the force experienced by that object or by that
Now, we are going to be looking at electric field due to a point charge. Now, what is the meaning of a point charge? A point charge is the same as a single charge. So, if you have a single charge in space or anywhere, and you are asked, what is the electric field due to this charge? And it's just one single charge. If you want to calculate the magnitude of the field or the intensity of the field, you are going to come from this formula that E is equal to F over Q. Remember that F is equal to KQ1, Q2 over R squared. On substitution, electric field due to a point charge will be reduced to E is equal to KQ over R squared. Or we are going to have it this way, Q over 4 pi epsilon naught R squared. Now, this is for a vacuum or air where there is no relative permittivity or dielectric constant. If we have a dielectric constant, then the dielectric constant is going to affect this epsilon naught, which may reduce the field, the intensity of the field. So let's assume the dielectric constant now, in this case, is equal to 1. So we are going to have this formula for electric field due to a point charge. So, where R is the distance, look at what we are saying now. Let's say we have a charge. The charge can either be positive or negative. So I won't put the charge or the nature of the charge. Then you say, what is the field at this point? Let's say P. So electric field at that point, this is distance, the distance between the field and the charge. We say the distance is R. So the electric field at this point now is equals to K times the value of the charge, KQ over the R squared. Now what is K? K is equal to 9 times 10 raised to the power 9 Newton meter squared per coulomb squared. That is the value for K. Remember this an approximate value. Actually, it's actually 8.99 exponential 9 Newton meter squared per coulomb squared. So remember, this charge can either be positively charged or negatively charged. So that's what we're having. So if it's positively charged, the field will be leaving. And don't forget, you have a positive charge. Electric field lines will be leaving a positive charge. If we have a negative charge, electric field lines will be coming into or going towards the negative charge. Don't forget that concept of electric field line. So we are going to look at this question now to calculate the field strength at a distance of 100 cm. Calculate the field strength or electric field intensity at a distance of 100 cm from a charge of 80 microcoulomb. From a charge of 80 microcoulomb. Calculate the electric field strength at a distance of 100 cm from a charge of 80 microcoulomb. So we said, how many charges do you have? You have just only one charge, which is this, and this is the distance. Now, remember I told you guys that micro is the same thing as 10 raised to the power minus 6. That will be coulomb. Then, converting this to meters from cm, you divide it by 100. If you have to convert from centimeters to meters, we divide the value by 100. So 100 divides 100, we're going to have 1 meter. That's what we're going to have there. Then K is approximately a constant number, that is 9 exponential 9. 9 times 10 to the power 9 Newton meter squared per coulomb squared. Then the electric field strength at that distance will be KQ over R squared, which is 9 times 10 to the power 9 times 8 t times 10 to the power minus 6 over 1 squared. So this is going to give us 9 times 10 to the power 9 times 8 times 10 to the power minus 5. 8 times 10 to the power minus 6 is 8 times 10 to the power minus 5. Now 8 times 9, what are we going to have there? 8 times 8 is 64. 64 plus additional 8. We're going to have something 72. We have 72 times 10 to the power 9 minus, that is plus minus 5. That will be 72 times 10 to the power 9 minus 5 will give us what? It will give us something 4. So this will give us 7.2 times 10 to the power 5 Newton per coulomb. So you don't need to solve it with your head from this place, because 1 square, this is why I don't include this one again. 1 square is equal to 1. So that's why I deleted the denominator. That will tends to 1. Numerator will tends to 1. So only the numerator will be active. So from this place, you can just use your calculator to round it up to get this answer. You don't actually need to start calculating with your head. So we're going to have 7.2 times 10 to the power minus 5 Newton per coulomb. That's what we're going to have. Now, we are going to look at electric field due to several charges. That is more than one charge. If we have 3, 2, 5, 6 charges, how do we calculate the electric field due to these charges? Okay, electric field due to several charges. Now, we are going to the class more deeper now, because this is where the actual work is. In this place, you are going to use your brain, because it's not just a straightforward evaluation. So we are going to be applying rules of vector additions here, because we are not going to be looking at just one field. Because when we have several charges or more than one charge, we're going to have more than one field. We have 2 fields. Remember, electric field is a vector quantity. So we're going to be adding fields together vectorially or using vector addition. Now, electric field due to several charges is done using the superposition principle, which is the vector sum of all the electric field present. The vector sum of what? All the electric field present. E.g., let's say I have 2 point charges separated by a distance. Let's say I have 2 point charges, positive, negative, separated by a distance. Let's say separated by a distance L, and you ask what is the electric field intensity at the midpoint of these 2 charges. You calculate the electric field intensity at their midpoint, or at the center of these 2 charges. So how are you going to do that? So we're going to have, okay, let me just take this as our, so this, remember this from here is L, from here will be L over 2, L over 2. So let me just take one as, let's take one as Q2, let's take one as Q1, this one as arrow 2, arrow 1. So arrow 2 is same thing as L over 2, then arrow 1 is same thing as the full distance divided by 2. Since it's the midpoint, what is the electric field at this point? Is the midpoint. So let me call the midpoint point P. So what will be the electric field at point P? That's what I'm trying to look at now. So this is not actually necessary here, but if I give you a question, say what is the electric field at the midpoint of the 2 charges? Please and please, we'll have to get the midpoint, or the distance between the midpoint and the first charge divided the full distance by 2. The distance between the second charge and the midpoint divided the full distance by 2. So before you get the electric field at this point, you are going to do something for me. Look how to solve electric field due to several charges. What you do, you will draw a field line from the charges in question to that point in which you are calculating the field on. So you draw field lines from the charges to the point in question. So the point in this question now is the midpoint. So you are going to draw a field line from this point to this midpoint. You draw a field line from this charge to this midpoint. That's the first thing you do. Then the second thing you're going to do for me here, you are going to get the direction of the field lines. Remember, when you get the direction of this field now, you can use a test positive charge. I don't want to use a test positive charge. I want to use concept of field lines to get this direction. Now remember, for a positive charge, electric field lines will be leaving. They will be coming out of a positive charge. So this will be the direction of this field now. So I'm going to call this one E1. It's electric field to Q1. Now, what about for this? For a negative charge, electric field lines will be what? Entering the charge, coming into the charge. So it's coming towards the charge. So I'll call this one E2. It is electric field due to charge Q2. So if you want to calculate electric field due to charge Q1, it will be K times Q1 over R1. The distance, which distance are you going to use? Distance between Q1 and that point you are calculating the field on. Then, what about our electric field due to Q2? It will be K times Q2 divided by the distance between the points and Q2, and you square it. So this will be your Q1, this will be your Q2. Now, what will be the net or total electric field at point P? What will be the total electric field at point P? The total electric field at point P will be the vector sum of these two fields that are present. Now, when you know vector sum, you take note of the magnitude of the field and the direction of the field as well. Now, what is the magnitude of this field? Is this? We're going to get the magnitude from this formula. So actually, in this formula, you take the magnitude of this charge. Take the magnitude of the charge. You don't add the signs of this charge to them. You don't add their signs. You just take the magnitude. Only take note of that. It's very, very important. It's very, very important. Then, after you have obtained the magnitude of this field, then you will now take note of the direction. Now, look at this direction, look at this direction. Now, from the concept of the Cartesian coordinate, we have that the coordinates take this shape. If this place is plus x, side is minus x, is plus y, is minus I, and minus y. So if I want to add up these vectors, I can use this Cartesian coordinate because we use it in the law of polygon force or resolution of forces or vectors. Now this is a vector I want to resolve about this point P. So look at the meeting point here. That is the center. Or that is where, if a vector is along this x-axis now, this will be their origin or meeting point. So the origin of these two vectors now is this point. Look at the origin. And this is the place we are calculating the field on. So if, look at the shortcut is just that. If a vector is pointing towards the positive x-axis, the vector will be positive. That is, if it's go to the right-hand side, to be positive. If it's go to the left-hand side, to be negative. If it's go to the upward side, to be positive. If it's go to the downward side, to be negative. That is the concept of the division of forces. But if it is going towards both y and x, we now have to resolve using resolution of vectors. I did that in my last class when I was doing the charges and Coulomb's law and superposition principle. It's just the same way. So if you look at these two vectors now, they are moving or traveling to the right hand side. Look at it, they're traveling to the right hand side. And the right hand side of this place is positive. So automatically, both E1 will be positive, and E2 will also be what? Positive. So if you want to add it up, we're going to have plus E1 plus E2, or E1 plus E2. It still give you the same thing. So both E1 and E2 will be positive, since they are going towards the positive S direction, or the right hand side. So this is just the best way to explain that. This is what we call resolution of vectors. So if you can do this, you are going to have the answer in a very simple way. So please, let's look at a very lovely example now. Very lovely example. Now, let's assume we have the question below. 2 point charges of 3 microcoulomb of plus 3 microcoulomb and minus 2 microcoulomb. 2 point charges of plus 3 microcoulomb and minus 2 microcoulomb are 10 meters apart, are 10 cm apart. Sorry about that. Are 10 cm apart. Are 10 cm apart. Obtain the field strength at midpoint between them. Obtain the field strength at midpoint between them, and also obtain the field strength at a distance of 4 cm from plus Q3 and 6 cm from minus Q2. I'm giving 2 questions now. I said you should obtain the field strength at where? at the middle of these two charges. That is the midpoint of these two charges. That is the first question. Then the second question is, obtain the field strength at a distance of 4 cm from this plus 3 microcoulomb and 6 cm from this minus or 2 microcoulomb. So let's see what we are going to have if we solve this. So let's go. For the question A, we have plus 3 microcoulomb, then we have minus 2 microcoulomb. And we have plus, this one is what? Negative. And they are what? They are 10 cm apart. Both of them are 10 cm apart. And it says we should calculate the field at midpoint between them. Let me call that point P. I'll call that point P. So I told you, the first thing you do, if I call this one Q1 and I call this one Q2, then the distance between these points in question, which is midpoint, between Q1 and that point will be R1. Then the distance between Q2 and the point in question, I will name it as R2. And I told you that R2 is L over 2, R1 is also L over 2, which is the full distance divided by 2. If it's the midpoint we are looking at. Remember the first question I called was the midpoint. So R1 will now be the full distance, which is 10 over 2. That will be what? 5 cm. This one is set as 5 over 100. When we convert it to meters, divided by 100, we'll have 0.05 meters. We'll have 0.05 meters. Then this other one will still be the same thing. Over 2, we're going to have 5 cm. So it has 0.05 meters. Now, what will be the value for our E1? E1 will be Q1 over R square. This is R1. Now, what is K? 9. Remember, K is what? Approximately 9 times 10 is per 9 Newton meter square per coulomb square. Remember that? Then, we're going to have 9 times 10 is per what? 9 times Q1. Now, if you want to use these charges, we don't apply their signs. No, look at what we're going to use these signs for. This minus and plus. Look at what we're going to use it for. If we calculate the magnitude from this formula, then we use the sign to get the direction of the field. Like this method I'm using now. I use signs to get the direction of this field I'm talking about. Now, if you draw a field line from this charge to this point, then what will be the direction of this field line? For a positive charge, the field will be moving away or directed away from the positive charge. The field will be leaving the positive charge. Then, for a negative charge, we draw a field line from this charge to this point in question. The field line's direction will be coming into the negative charge. So we don't have to like this. So this will be our E2, this will be our E1. So that's what we send for, to get the direction of the field. Then this formula will give us the magnitude of the field. So if I combine the direction and magnitude together, then add them together, then we'll now call it vector addition, or vector summation, or vector sum. So the Q1 will be, I'll just take the magnitude. Magnitude means remove the sign and pick only the value. So I'm going to have, the value is 3 times 10 to the power minus 6. I hope you can remember that. Times 3 times 10 to the power minus 6 coulomb. So one is minus 2 times 10 to the power minus 6 coulomb. Because that, you remember that. Then over, what is the distance between Q1 and this point we're talking about? The distance between this point and this Q1 is what? 10 divided by 2, which is our R1, 10 divided by 2. And the distance between this place and this place is 5 cm. The distance between this place and this other place, this charge is also 5 cm. Because the diagram is already getting complex. So that will be 0.05 squared. So what will be the answer to this? If you solve it, and for your calculator, you are going to get the answer. Then, our E2 will be KQ2 over arrow 2 square. This will give us 9 times 10 raised to the power 9 times our what is q2? Minus 2. Remember I told you if you want to apply this formula, just omit or throw away the sign and pick the value, the magnitude, the size of the charge only. Then do away with the sign. Don't use the sign. So we're going to have 2 times 10 to the power minus 6 and over the distance is 0.05 squared. So if you use your calculator to run this, you're going to have the answer. Now, what will be the electric field at point P? The total electric field at point P. The total will be the summation of this and this. Will sum up the two. Both their magnitude and their direction will be taken into consideration. So, taking both the magnitude and the direction into consideration, we are going to have, now what is the magnitude of this one? The magnitude will be obtained from this place. Now we are going to have the magnitude. Then the direction is to the right hand side. So it's moving to the right hand side. So this E1 will be positive since it goes to the right hand side. I've already explained that. Then what about the E2? Also moving towards to the right hand side. So this E2 will also be what? Positive. That's positive E2. So if you obtain the value of E1 and put it here, put the value of E2, put it here, then we'll get the final answer for the electric field at point P. So let's run this with our calculator, then obtain the answers, move to the question P, then we move to the next agenda. Alright, if you solve it with your calculator, we will have 1.08 exponential 7 Newton per coulomb for this E1. Then you'll be having E2 as 7.2 exponential 6 Newton per coulomb. Then the final electric field or the total electric field at that point P, which is the midpoint, will be your plus E1, since it goes to the right hand side, plus E1 and plus E2. Since E2 is also goes to the right hand side, so it will be plus and plus. Assumed this one was a negative charge, then this direction will change. This one will be entry. So it will be, if I want to find the total of this one now will be minus, because this one is moving to the left hand side now. Be minus E1, then this one is going to the right hand side plus E2. Now if this one is positive, then this direction is going to change. It will now be leaving the chart. It's going to be negative E2, also negative E1. So we're going to have minus E1 plus minus E2 as the final answer. But the one we have here is just plus, while this one is minus. So the directions are as follows. This one will be leaving, then this one will be coming into or entering the chart. So this one will be positive, that will be positive E1, then plus positive E2. That's what we're going to have. That's how I'm having plus E1 plus E2 for this question. So what is our E1? This plus the E2. We're going to have this one as your final answer. Now, for the question B, or the big part of this question, what you are going to do, you are going to have something like this. You have plus, you have minus. That is minus 2 microcoulomb. You have plus 3 microcoulomb. Then I ask you, what is the field strength at a distance of 4 cm? That is 4 cm from the plus 3 and 6 cm. Because remember the total is 10 from this minus 2. So here now, what will be electric field at that point? What will be electric field at this point? If you draw a field line to this place, then this direction of this field line is going to be away from this positive side and moving towards the negative charge. So this one will be your E1 or be your E2. So the electric field at this point P, if you do it, I want you to do it yourself, then you are going to have 2.2 times 10 raised to the power 7 Newton per coulomb. Try and see if you can do that. It's a very simple case. It's a very, very simple case. Now, there is a question I would like to look at now. There's a question I would like to look at. Alright, let's look at this question. The figure below shows 3-point charges. Charges Q1 equal to Q2 equal to Q3 are all equal to plus 2 microcoulomb. Obtain the electric field strength at point P
obtain the electric field strength at point P. What will be the strength of the electric field at point P? What will be the strength of the electric field at point P? So that's what I'm going to do now. Let's do that. So before you do this, from the concept of field lines, we're going to field at this point. The relation between P and Q1 is 6. The relation between P and Q2 is 6. The relation between Q1 and Q2 is also 6. 3 plus 3, that will be 6. So automatically, this shape is describing an equilateral triangle. This one is 6 cm, 6 cm, 6 cm. So the midpoint, these charges are the midpoint. So that the distance between these points and the midpoint can be obtained from Pythagoras theorem. So let me call this one x. Let's call this one x. Now I want to forget the distance. Then I will obtain the magnitude of all the charges. I'll get their direction, and I will get how to resolve them. So let's go. Let's try to see what we're going to have. So we're going to be having something like this. From Pythagoras theorem, we're having this shape here. This shape is what we're having. So this one is x, this one is 6, and this one is 3. Then c squared must be equal to the square of the hypotenuse must be equal to the sum of the square of the other two sides. Must be equal to s squared plus 3 squared. That is s squared will now be equal to what is c squared? 36. If this plus 3 crosses this equal to sign, change to minus 3, and minus 3 is going to give us minus 1. Then 36 minus 9, what are you going to have? 36 minus 9. 36 minus 9. What are you going to have? I think I'm going to have something like 27. That's what I'm going to have. And x, automatically x will now be equal to, you take the square root of this side, take the square root of both sides, this square will go, then x will now be equal to root 27. X will be equal to root 27. That is going to be x. That is going to be x. So, what is the next thing I'm going to do now? I've already obtained the value for x, which is 27 cm. 27 cm. The answer here is 27 cm. So we're going to convert everything to meters, then obtain the magnitude of the electric field from Q1. Remember, electric is going to come from Q1, electric will come from Q2, electric is going to come from Q2. So calculate the magnitude from KQ1 over R squared. Then after that, we'll get the direction. Now let's get the direction of the field at point P. Like look at this. You draw a field line to this point now, this charge. The field line will be leaving, so it's leaving this charge. What about this? It will also be moving away from the charge. So it will be directed away from this charge as well, because they are positive charges. Be directed away from the charge. So this one is moving, going upward, and go this side, other side. So if I try to move this one out, extrapolate it upward, now I'm going to have something like this. If I extrapolate it onto this side, I'm going to have something like this. I'm going to have something like this. If I extrapolate it upward, I'm going to have something like this. So this one will be our E3, is electric field coming from Q2, to be our E1, electric field coming from Q1, that will be our E2, electric field coming from Q2. That will be electric field coming from Q2. So the next thing I'm going to do here will be to obtain the values of this field. Now, remember for equilateral triangle, this angle, and this angle, and this angle are all 60 degrees. I don't know if you can remember that. All the internal angles of equilateral triangle are all 60 degrees. So automatically, this angle here, so this full angle here, okay, automatically half of 60 will be what? What will be half of 60? 30 degrees. What about half of this other 60? 30 degrees. So automatically this half will be 30 degrees. This other half will also be 30 degrees. 30 degrees. So then 30 degrees, 30 degrees. Then you're already good to go. So since I've gotten the angles made by these vectors, so we can resolve these vectors now to the horizontal direction. We also resolve them to the vertical direction. We look for the resultant or the total force at this point P. So look at what we're having, the other vector at that point P. Now look at what we're having here. I'm something like this.
Like a point and the vector is going to this direction, and the vector is E1. Another vector is moving towards this direction, that vector is E2, moving towards this direction, that vector is E3. Then another vector is moving upward, and that vector is E2. From vector is 30 degrees, so it's also 30 degrees. It's also 30 degrees. So if you want to do this, what you have to do is just do something like, just take a 4 cardinal or a Cartesian coordinate to that point, then you resolve. So you can use this 30 to run your resolution, there's no problem. But remember, the full angle or the full quadrantal angle is 90. So if you want to get this angle now to the horizontal, because the concept you use angle to the horizontal. So if you use the angle to the horizontal, you just remove this one from 90, you have 60 degrees. Same thing, you have 60 degrees. You are going to have 60 degrees. You have 60 degrees there. So what are we not going to have as our answer? We don't know E1, we don't know E2, and we don't know E3. And remember, the distance between this point and E1 and E2 are both the same thing. So E1 and E2 automatically will give us the same answer. So let me calculate for what is E1. E1 will be K cube 1 over R1 squared, which is 9 times 10 to the power 9 times, what is the value of this charge? All of them equal to 2 microcoulomb, that is 2, and 10 to the power 6, divided by, what is the distance between this and this point? 6 cm. Now, how do you convert 6 cm to meter? Divide it by 100. Divide 6 by 100, you will have 0.06 squared. Then E3 will also be KQ3 over R3 squared, which is 9 times 10 to the power 9. Okay, now what is going to be the answer to this? Let me leave a space for that. So we will have E1 to be equal to, if you solve this calculator, you will have answer. And let's say we have E3, which is KQ3 over R3 squared. That will give us 9 times 10 to the power 9 times, what is Q3? Q3 is still the same thing as 2 times 10 to the power minus 6, then divided by our ROT is the same thing as 0.06. So look at it, ROT, the distance between Q3 and this point is 6 here. And this one is 6 over 100, that is 0.06 meters. Use meters to solve. So if you solve it, you will have this answer. Then what about our E2? E2 will be equal to our KQ2 over R2 squared. So what will this give us? Remember, E2 is in third form, this is 27. So let's move down to decimal, then put it to this place and see what we are going to obtain or see what we are going to get. Let's try that, see what we are going to get. If you check for the decimal equivalent of this, you will have 5.2 cm approximately. So if you divide it by 100, you will have 0.052 meters. That's what you will have for that. Then the R2 now, the sum between this Q2 and this point is this X, is now 5.2 cm, with 0.052 meters squared. So if you solve this, you will have this. Solve this, you will have this. Solve this, you will have this. Both, I already told you, E1 and E3 will be the same, since their distance from this point and the two charges are equal. So we already know our E2, E1, E3 now. So we're going to plug them into this place. Our E3 is this, E1 is this, E2 is this. So the last thing we're going to do here now, from resolution of forces, resolution of vectors. I'm just using forces because the force is a vector. So for resolution of vectors, we are going to have something like the component of this vector in the x direction, the sum of all the components in the x direction. So this one means the sum of all the electric field in the x direction. So that will be, remember I told you this side is positive, this side is negative. We have minus 5.0 times 10. Okay, this side is positive, that is plus 5.0 times 10 to the power 6. Then you use to multiply cosine of the angle between this and this positive x direction, or the sine of the angle between this and this y direction. If you want to use cosine for x, ensure the angle between this and the x direction. Then you are going to have cosine 60. Then remember this one is going to the left hand side, this one will be negative now. Minus 5.0 times 10 power 6 times cosine, you are going to on the x direction is 60. Then both of them are equal. So you subtract it from this, you have 0. You need to get cool. So you will have in this direction, the becomes up. Okay, what about this other one? What about this one? Now this one is truly y-axis. It's truly vertical. So since it's in the y-axis, it's not we are not going to have any x component for this. Or you can just also say plus our 6.7 times 10 to the power 6 cos 90. Now, if you do cos, because the distance, the angle between this one and this direction is 90 degrees. And if you try cos 90 is 0, everything else is 0. So it will not be nice, or it is not even important to even add it. Since this one is already in the y direction, it will not have any x components. And any force in the x direction that is truly horizontal will not have y components. Take note of that. It's very, very important. So everything here will still give you 0. This one right, there's nothing here. This one is 0 since it's truly y. So that will not give you anything. Then, what about the sum of all the electric field in the y direction? That will be equal to, no, this one is already truly y to the opposite side. There's no need to use to multiply anything. Or, you are still free to use to multiply sine. But look at it. If we are using angle between the vector and the x-axis, we'll be using cos for x direction. Then we will now use sine for y direction. But if we are using the angle between this vector and the y-axis, we'll be using sine for x direction. We will now use cos for y direction. Please let me explain that to you. If I'm using, you can use any of the angle, you get the same answer. Very clear. If you are using angle between the vector and the x-axis, which is the horizontal axis, then you are going to use cos for the component of x, or the amount of vector going to the x direction. We're going to use cos for that. So we are going to use cos of the angle, cosine of the angle, cosine of the angle for x component. That is, if you are obtaining or using the angle between the vector and the x direction. Then for y, you can see this is that same angle you use for this x. Then as you're using cos in this one, you're going to use sine for this one. Look at what I'm going to do now. I'm going to have this, now I'm going to have, then look at it, E1 is going to the opposite side, it will be plus E1. Okay, what is E1? E1 is 5.0 times 10 to the power 6. Sine now, 60. Then, this one is also going in the opposite side, that is positive. Plus, remember in the upper side, thank God this diagram here, in the upper side, y is positive. The down side, y is negative. The right hand side, x is positive. Left hand side, x is negative. So, plus, this one now, okay, this one now, that will be 6.7 times 10 to the power 6. Then sine 90. And the angle between this and the x-axis is 90 degrees. But even though you don't, if a vector is truly vertical, just take the value of the vector. There's no need of multiplying it with any angle because you still give you the same thing. Sine 90 is 1. 1 times this will give you the same thing. So there's no need of multiplying it by any angle. Then this one is still in the upper side, so we are going to have plus 5.0 times 10 to the power 6 sine 60. So everything here is going to give me 1.54 times 10 to the power 7 Newton per coulomb. This is vector in the y direction. So look at this. Again, if I use the angle, if I'm going to use 30 degree now, which is the angle between this vector and the y-axis, this cos I will use sine 30, sine 30. Then this one I will use sine 0. Why am I going to use sine 0? Because the angle between this line and this vector is 0. Is 0. So we don't use 90 here again. The angle between this y-axis and this vector in the y-axis is 0. So you use sine 0 here. Then for this you use cos. You use cos 60 here. You use cos 30. Since you are now using this 30 degree, you use cos 30. Then this one now will be cos 0. Since you are using cos for y and your turn this line. Angle between this line and this same line is 0. Use cos 0. Then for this one you use cos 30. You have the same thing, exactly the same thing. Cos 0 will give you 1. So I would advise you to always be using angle between the vector and the horizontal, so that the horizontal will just be cos, the vertical will be sine. What is the angle between this and the horizontal? If you have the angle between the vector and the vertical, just remove it from 90, you get the angle between the vector and the horizontal to eliminate confusion, so that it will be very, very lovely. So the total electric field at point P now will be the square root of the total electric field to the x direction square plus the total electric field to the y direction square. So this is going to give us, this will be giving us something nice. That will be our electric field at point P will now be equal to the square root of 0 square plus 1.54 times x power 7 squared. So everything here is going to give us 1.54 times 10 to the power 7 Newton per coulomb. Newton per coulomb. Or if I want to put it in vector form, I will say electric field at point P is 1.54 times 10 to the power 7 G, because it's going to be y direction, and the unit vector for y direction is G. So just put it this way, Newton per coulomb. Newton per coulomb. So please, the angle between this vector moving in y direction and the horizontal now will be 90 degrees. That will be 90 degrees. So please, I beg you, check this thing over and over again in case you don't understand it. And you are free to watch this video over and over again in order to get the full understanding. Alright, electric field due to a dipole. Now, in electric physics, we have what we call a dipole. Now, what do we mean by a dipole? A dipole is just a pair of equal and opposite charge. A pair of what? Equal and opposite charge. What do we mean by that? We have two charges. The magnitude of these two charges are the same, while their signs are opposite. That's what I'm trying to say. So a dipole is a pair of equal and opposite charge separated by a distance. Let's assume we have something like this. Let's say we have two charge bodies, charge 1, charge 2. If one is positive, this one is negative. Both of them will have the same magnitude, but one of them will be positive, the other one will be negative. That's what we call a dipole. The distance between them, we can call the distance between them. Let me call the distance between these two dipoles now. Let me call the distance between these two dipoles. I will call it this. I will call the distance L. We call the distance L. Then this is the line of action of these two dipoles, and we're going to have the midpoint of the dipole. Now the distance from each dipole from the midpoint, let me call it A. Now Q, this dipole, this charge, this one of the two charges to the midpoint, I'm going to call it A. Now I can tell you to look for something for me. Number one is the electric field at a perpendicular distance R. Let me call this point P. We call this one point P. If we add this, so that distance R from this midpoint. So we call that a perpendicular distance R. This one, because it is perpendicular to this line of action of the force between these two charges. So because distance R is distance from their midpoint, then we can also ask you for electric field at a prolonged distance. The long distance from the midpoint, that is from this midpoint to this point. Let me call this one Q. Call this one Q. Okay, or let me just use small letter Q. Small letter Q. So also ask for electric field at that point. This is TR. This is TR. Now, this one is prolonged distance or parallel distance to the midpoint of the dipole, while this arrow is the perpendicular distance to the midpoint of the dipole. So, as for that field, electric field from this charge will be entry, while this one from this other charge will be leaving the charge, going this way. So this will be E1, this will be E2. Then, what about this other one? Draw a line of action. Just draw field lines to this point, draw field lines to this point, draw field lines to this point. Then, the electric field will be leaving, so we're going to have something like this. For this, You have something of this nature. Then this other one will be coming in. Why? Because this is a negative charge. If will be entering negative charge, we're leaving a positive charge. So if you complete this as a parallelogram, this is what we are looking for, which is electric field at point P. That's what we are looking for. So we are going to look for this electric field at point P, and also look for electric field at point Q. Look for electric field at point Q. So let me use another point for this. Let me use point K. There we go. K is used for Coulomb constant. Okay, let me use point let me use point R. Okay, let's point H. Electric field at point H. When you are electric field at point H, that will be just better. So that is just a point. We use that as a point. So electric field. Okay, before we look for this electric, look at this electric field at this point P and this point H. There's what we call electric dipole moment. Electric field dipole moment. Now, a dipole will have electric field dipole moment of magnitude P equal to 2AQ or L times Q. What is L? L is same as 2 times A. A plus A will give us 2A, which is the full distance L. So 2 times this distance times one of the magnitude or one of the charge or the magnitude of any of the charge will give us a value or a quantity called electric field dipole moment. So this P is called electric dipole moment and is the what? The product of the distance between the two dipole and the magnitude of any of the charge. Now, this Q is the magnitude of any of these charges, but the two charges are going to be the same but different in sign. So if you throw away the sign and pick the magnitude will still be the same thing. The L is the distance between the two charges. So we can define our electric field dipole this way. Electric dipole moment. Field dipole moment. So if they ask you what is the electric field dipole moment of this charge, you should be able to solve it. Now, what about electric field at point P? What is the electric field at point P? The electric field at point P, EP, will be equal to Kp, K times P, remember P is electric dipole moment, over R squared plus A squared, everything is part T over 2. That would be electric field at point P from derivation. That will be electric field at point P. But if your arrow is far greater than A, arrow is now far greater than A, in which A will now be something like negative, or A will be so small that we will not add much value to this quantity, we can turn this A to 0 such that our EP will be reduced to Kp over arrow Q. That's what we're going to have. If our arrow is now far greater than A, we turn this up to 0, we put 0 here, 2 we cancel 2, we have arrow Q, take Q over arrow Q. But electric field at point H, EH, electric field at point H, that is, this is the electric field at a perpendicular distance from the midpoint of the dipole. That's what we have here. The electric field at a prolonged distance from the midpoint of the dipole, or parallel distance from the midpoint of the dipole, is given as 2k arrow P over arrow square minus A square, everything is power 2. That's what I'm going to have if you solve this question. Now, if your arrow is also far greater than A, arrow is not far greater than A, you can take this A or just neglect it. Just throw it down A. Then you will be having your EH to be equal to 2kp over arrow Q, which is almost 2 times the electric field of the dipole at the perpendicular distance they are made from. Check. Both this and this are always the same thing, but this one is just 2 times this second one. That's what we are having here. Now, let's look at this question. Let's look at this question. Very question. Very question. 2-point charges of plus 4 microcoulomb and minus 4 microcoulomb, of plus 4 microcoulomb and minus 4 microcoulomb, are separated by a distance of 20 cm. A distance of 20 cm. Are separated by a distance of 20 cm. Obtain the electric dipole moment. Obtain the electric field dipole moment
of this charge, what's the dipole moment of this charge, and the first one is what's the dipole moment of this charge. Then the second question I'm going to calculate now is also obtain the electric field at a perpendicular distance, of 50 cm from their midpoint. Also obtain the electric field at a perpendicular distance of 50 cm from their midpoint, that is EP. I'll have that. Then the third, that is for C now. Also obtain the electric field at a prolonged distance of 100 cm from their midpoint. Also obtain the electric field at a prolonged distance of 100 cm from their midpoint. So this is the question we're going to go through now. Now the first one I have here is electric field dipole moment is equals to L times Q. Now what's L? At the L here, which is let's as 20 over 100 equals 0.2 meters. Now, what is Q? Q will be the magnitude of any of the charge. That means remove this side and pick any of the value. You see before microcoulomb, which is 4 times 10 to the power minus 6 coulomb. So therefore, our P will be equal to our 0.2 times 4 times 10 to the power minus 6. That's what we're going to have there. So if you solve this value, we're going to have, okay, let me move this one to a standard form. So I'm going to have 2 times 10 to the power minus 1. So if you move this one to this place, you're going to have something like this. Then times 4 times 10 to the power minus 6. So 2 times 4 gives us 8 times minus 4. Okay, look at 10 to the power minus 1 times 10 to the power minus 6. That will be minus 1, minus 6, that will be minus 7 coulomb meters. Coulomb meters, because it's L or meter coulomb. It's coulomb or meter that resisted this source or this electric field dipole moment. So I call the unit coulomb meters. Now, that's just the first one. What about the second one? What is the electric field at a perpendicular distance of 50 cm from the midpoint? What will be the electric field at a perpendicular distance of 50 cm from the midpoint? So the same thing as 50 over 100, that is 0.5 meters. 0.5 meters. And what is the mean distance of these two dipoles? Would you say? What is the mean distance of these two dipoles? The total distance of the dipole, they are 20 cm apart. The mean distance will be the total divided by 2. So in this place now, our A is L over 2. Take note. Our A is total divided over 2. So take note of that. So that will be, what is L? L is 20 over 2. That will be 10 cm. And divided by 100, that will be 0.1 meters. 0.1 meters. Now, let us obtain the field at a perpendicular distance from the midpoint. Let us obtain the field at a perpendicular distance from the midpoint. The field will be E is equal to what? It's equal to what? Kp over what? Arrow square plus A square. Everything is about what? 3 over 2. So, we're going to have K is what? 9 times 10 to the power 9 times P is what? 8 times 10 to the power what? Minus 7 over arrow is what? 0. What? What is our arrow? Arrow. 0.5 square plus, what about our A? Our A is what? 0.1 square. Everything is about what? 3 over what? 3 over 2. So we solve this one very well. We will have the answer. We will calculate calculator. Just solve this. We will have the answer there. So before we go to that answer, to write the answer, let me quickly solve the third one. The third one is electric field at a prolonged distance of 100 cm from the midpoint. This is 100 over 100, which is 1 meters. We want to divide it to meters divided by 100. So the electric field at the prolonged distance now will be what? 2k arrow p over what? Arrow square minus what? A square. Everything is for what? 2. That will give us 2 times 9 and 10 is for what? That's 9. That's 10 is for 9 times arrow. What is our arrow? The prolonged terminal is 1 times 8 times 10 is for what? Minus 7 over our arrow is 1 square minus what is A? Our A is what? 0.1 square, 0.1 square, everything is power what? 2. If you solve this one, you will have your answer there. You will have your answer there. So let's solve this with our calculator now to check the answer we are going to have. So let's solve and see. Alright, you solve this very well. Let me feed at a perpendicular distance of 50 cm, which is actually P on the midpoint, will be 2.77 times 10 power 4 meters per coulomb. Then find out of a prolonged distance of 100 cm from the midpoint. Remember this formula will be 1.47 times 10 power 4 Newton per coulomb. This will be the respective electric field. Now, in our next class, we'll be looking at electric field due to continuous distribution of charges. Look at electric field due to charge wire or lines of charge. We look at electric field due to a charge ring, a charge disk, a charge sphere. Then we also look at Gauss law. So please ensure you follow up our next class and watch this video over and over again. See you guys in our next class. God bless you. I love you. Thank you.